Hello math friends, this is AP Calculus section 5.2 day 1. So today we are going to talk about what a definite integral is. We learned in the last section that we can use limits when we're trying to find the area under a curve or distances traveled by an object. We'll soon learn that limits of this type also arise when you're trying to find lengths of curves, volumes of solids, centers of mass, force, work, other quantities. Remember, calculus is applied math, right? So all of these things involve integrals. And this type of limit is given a special name and notation, which is called the definite integral. So there's a lot of jargon right here. Don't worry so much about that. Here's the limit notation of the function. Let's kind of talk about what this means. This is the limit as n goes into infinity, meaning n number of rectangles, where n goes to infinity, or an infinite number of rectangles, the sums of the height of the rectangle times the base of the rectangle, right? That's the form of it in limit notation. What does it look like in integral notation and calculus notation? It looks like this. So we've got this symbol right here, which looks like an elongated S because an integral is a limit of sums, okay? And then you've got your function f of x, and then you've got this dx, okay? So the f of x is kind of like the value of the function, and then the dx is kind of like the base of the rectangle, right? So those are the parts of the translation from limit notation to integral notation, okay? And if the limit does exist, we say that f is integrable on the interval a to b. And so the limits of integration here go along that integration symbol from a to b, okay? So all of the examples that we did so far, our curve was always completely above the x-axis. But what if the curve that we are trying to find the area of lives both above and below the x-axis, as in this picture right here? Well, if our function takes on both positive and negative values, then the areas between the function and the x-axis above the x-axis would be positive, and the areas that we'd calculate between the function and the x-axis where the function is below the x-axis, the heights of your rectangles would have a negative value, and so those areas would be negative. And so basically the idea here is that a definite integral can be interpreted as a net area or a difference of areas. Okay, so if we look at this picture here of the integral from a to b of f of x dx, we're looking at area 1 minus area 2, where area 1 would be the region or regions above the x-axis and below the graph of f, and area 2 would be the region below the x-axis and above the graph of f, right? So just kind of that idea of the integral being the net area. Again, areas above the x-axis are positive, areas below the x-axis are negative. So let's take a look at our first example. It says, if f of x is equal to x squared minus 2x on the interval from 0 to 3, evaluate the Riemann sum with n equals 6, taking the sample points to be right endpoints. Okay, so we're doing right endpoint rectangles. What does the Riemann sum represent? Illustrate with the diagram. So I think it makes the most sense here for us to actually start with the diagram. So let's draw an x and a y axis. Okay, and our function, I just went ahead and I graphed it previously. Okay, it crosses the x-axis here. It's at 1, negative 1. It crosses the x-axis at 2. And it's at 3 at 3 here. So it looks something like this. Oops. Sorry, it should be a little smoother, but you get the idea, okay? And so if we're going to be doing right endpoints and they want n to be 6, the first thing we should find is our delta x. And again, our a to b, or our b minus a, is going to be 3 minus 0. divided by the number of rectangles, which we were told is 6. So 3 over 6 is 0.5, right? So that tells us that the change in x, or the bases of our rectangles, are going to be 0.5 units long. Okay, so let's mark this off a little bit here, a little bit further on our x-axis. So this is 1, this is 2, this is 3, so that would be 0.5, 1.5, and 2.5. And so if we are trying to find right endpoints, I'm going to go ahead and I'm going to draw my rectangles in here with right endpoints. So here's my right endpoint. And then this next one is kind of goofy because the right endpoint would be right here. So when I draw it, there's no rectangle there. It's just a straight line. And then here my right endpoint would be there, and here my right endpoint would be there. Okay, so these are the areas. And again, technically there's no rectangle between 1.5 and 2. It's just kind of a straight line there. And so the 3 rectangles right here, right, this area is negative because they are below the x-axis. And then these 2 rectangles right here, area is positive because they are above the x-axis. And our interval boundaries obviously are going to be at 0.5, at 1, at 1.5, at 2, at 2.5, and at 3, because those are the, the right endpoints of our rectangles. So when we calculate our area is going to be, and again, all of the rectangles have a delta x of 0.5, so I'm just going to put that out in front, and then I'm going to put all of the heights in the brackets. So the first height would be at f of 0.5. The second height would be at f of 1. Third height would be f of 1.5, because every 0.5 we have another rectangle. F of 2, f of 2.5, and f of 3. Okay? And so then we know the function. The function is f of x equals x squared minus 2x. So we have to plug 0.5 into the function, 1 into the function, 1.5 into the function, so on and so forth. So I've taken the time to do that, and I have those values. So f of 0.5 is negative 0.75, because again, it's below. We expect it to be negative. F of 1 is negative 1. F of 1.5 is, again, negative 0.75. F of 2 is 0. F of 2.5 is 1.25. And f of 3 is 3. So we add those numbers up and we multiply by 0.5, and we get that our area is equal to 0.875. Okay, and again, this is already our net area, right? Because we've basically considered the areas below the x-axis to be negative and the areas above the x-axis to be positive. All right, so let's kind of write down what that means. This area represents an estimate of the area between the curve and the x-axis. Areas between x equals 0 and x equals 2 are negative, and areas between x equals 2 and x equals 3 are positive. Okay? All right. So now that we've kind of practiced this idea of finding areas using left endpoints, using right endpoints, using midpoints, and we've done enough examples, I think that you have started to see hopefully that midpoints definitely give us the best estimate. And so did all of the mathematicians of the world decide that. And so they came up with this idea of the midpoint rule that basically just spells out how to find the area under the curve using rectangles with midpoints, right? So delta x is still your b minus a over n, and you're just taking, the base times the height of each of the rectangles, where the midpoint is going to be halfway, between, the base of each rectangle, between the endpoints of each rectangle, okay? So example 2 says use the midpoint rule with n equals 4 to approximate the value of the integral to 4 decimal places. And we're trying to figure out the area under the curve of the function, the square root of x cubed plus 1 between 2 and 10. Okay, so I'm not even going to draw a full picture of the function, but I am going to sketch a picture of the x-axis just so that we can talk about our rectangles being midpoint rectangles, right? So if we're looking at the area under the curve between x equals 2 and x equals 10, and we're going to divide this into 4 rectangles, okay, so we kind of have that spacing right there. If we're going to divide this into 4 rectangles, so our n equals 4, then our delta x is going to be equal to b minus a, so 10 minus 2 divided by 4, which is 8 over 4, which is 2. So basically, the base of each of our rectangles is going to be 2 units long, right? So from here to here, there to there, there to there, and there to there. Okay, so when we figure out where our heights should be for our midpoints, that tells us that they should be at x equals 3, at x equals 5, at x equals 7, and at x equals 9. Okay, that makes the heights of our rectangles at those locations. Okay, so then our integral, we're going to use our calculus notation now. So our integral from 2 to 10 of the the square root of x cubed plus 1 dx is going to be approximately equal to, because again, we're estimating it with rectangles. We know our delta x is 2 for all of our rectangles, right? They're all going to be 2 units long here. So 2 times, and then we just have to calculate those heights. So f of 3 plus f of 5 plus f of 7 plus f of 9. So then we grab our calculator and we plug 3 into the function. So 3 cubed plus 1 would be 27, plus 1 would be 28, square root of 28. So we end up with 2 times. This is the square root of 28. F of 5 is the square root of 126. F of 7 is the square root of 344, and f of 9 is the square root of 730. And again, then you grab your calculator, you add those 4 values together, you multiply by 2, and we get that our area is approximately equal to 124.164, 3 places past the decimal, units squared. Okay, so there's our area approximation using midpoint rule with 4 rectangles for that particular curve. All right, so the next thing that we're going to do is kind of look at how can we go from that Riemann sum limit notation back to integral notation. And so we had that definition in the beginning, the definition of a definite interval on the first page of our notes. And so here it kind of is again, and it's sort of explaining how we can rewrite something that is in that limit Riemann sum notation into integral notation with our integral symbol, okay? So again, keep in mind that the change in x, this is represented by dx in our integral form. The 2 to 6, that's going to be our limits of integration. So a is 2 and b is 6. And then our function is what we see after our summation notation. So in this case, natural log of 1 plus x squared. So if we're going to write this in integral notation, we need our integral symbol, our limits of integration, our function x, sorry, I forgot the x, times ln of 1 plus x squared. There's our function. And then don't forget, you always need that dx to represent that base of the rectangles, or that delta x, okay? So this is how we can rewrite this function in integral notation. The second one, same idea. So again, remember that change in x is represented by dx. In this case, our a would be 1, our b would be 8. And so we have the integral from 1 to 8. Our function is the square root of 2x plus x squared, and then we need our dx after our function. Okay, so these two exercises, these examples, were just asking us to change from that limit notation back to integral notation. And most of the time, we will be working in integral notation. So just understanding that in terms of finding areas using rectangles, that the function itself represents the height and the dx represents the base, and that's how we calculate our areas of our rectangles.